Good morning, Patel sir.
Good morning, sir.
I am Motilal from GC Jalawad.
Yes, sir. I know. Yes, sir. Welcome, sir.
Okay. Photo session is completed or yet to be?
No, it will start at 11, sir.
Okay.
Okay, welcome, sir.
So much. Thank you, sir.
Okay, welcome, sir.
Good morning, English sir. Hello. Sir, am I audible?
Yes, sir, you are audible.
Give me a minute, ma'am.
Hello, good morning, sir.
Good morning, English sir.
Yes, sir, you are audible. Perfect.
Okay. Sir, give me just a minute. I shall be starting.
Okay, no problem.
Within 1 minute.
ठीक है, रजनी, start.
Okay, so I'm presenting my screen now.
Sir, before that, let me introduce you to all the participants.
Okay.
A very good morning to all of you. My name is Rajni Chaudhary, currently working as Assistant Professor at Engineering College, Banswara. I heartily welcome all the experts, participants who have joined us for this FDP. Today is the third day of FDP, which is organized or sponsored by the TechCube Third. The FDP is on the topic Recent Advances in Composite Material. So starting with our first session, let me introduce you all with the expert of our first session, Mr. Bhupesh Goyal. Sir is currently working as Assistant Professor at Parul University, Barodara. Sir has more than teaching experience of 9 years. His skills include 3D prototyping, CNC programming, and NC software. Sir has also worked as production supervisor at Becto Chemical Consultant and Engineering Private Limited. Sir has done his MTech from Gujarat Technological University, Ahmedabad in CAD CAM. Sir, you're most welcome. It's our honor to have you, sir. So you can start with your presentation now.
Okay, thank you for introducing me.
Thank you, sir.
Okay, so I shall be presenting now. I hope my screen is visible.
Yes, sir.
Okay. So good morning to everyone. I'm Bhupesh Goyal. Right now I'm pursuing my PhD from MS University, as well as I'm working in Parul University as assistant professor. So we are going to talk about the particulate reinforced metal matrix composites. Now, there are certain different types of composite which are available in market. Now, how to manufacture them, that is again a big task. Correct. So, we are particularly dividing them according to their methods of manufacturing. Correct. So, we're having stir casting, which is one of the, you can say, not conventional one. It is something different. So, we are going to talk about the stir casting. Now, in my presentation, I would be taking the introduction to the metal matrix composite, and then I would be discussing about the case studies, which we have already worked since 7 to 8 years around. So that we would be discussing. So let us begin with this now. So what generally we consider as a composite material. So when you are manufacturing a material with different phases and which properties are not same. So when you are producing such a material, you are making it, then it is known as a composite. Okay. Different phases, it means, let's say, if I'm taking the example of aluminum alloy, when I'm saying alloy, it means the phases are in melting condition. Okay. So in liquid condition, we are making the material and we are fusing them, you can say. But when we are talking about the composite material, they are in different phase. It means the aluminum would be in melting condition, while other constituents, it may be silicon carbide, it may be aluminum oxide, it may be magnesium oxide, it may be anyone, but they would be in a different phase. Okay, that is a solid phase particularly. So when we are making in such a manner, that it is known as composite material. Now we are not going to talk about the plastic composite, that is FRC, FRP. We are particularly focusing on metal matrix composites. Now as you can see, if this is the your parent material, that is your aluminum, and if you are putting the particle reinforce in this manner, then we are taking telling it particle reinforced metal matrix composite, PRMMC. It's abbreviation of it. Now, where the composites are falling in the H pi chart, because whenever we are talking about the Young's modulus and density, definitely these are the two basic properties of any material which we are focusing upon. Correct. So, any analysis you are making or any calculations you are making, Young's modulus and Poisson's ratio. So, these are the two very important properties of any material. Now, let's say we are having some conventional materials which are metals. Okay, so for that we are having our Young's modulus of elasticity and Poisson's ratio, which is a standard. If I take the example of steel, it is, let's say, 0.3 of Poisson's ratio, and Young's modulus is of around 200 GPa, gigapascal, or you can say 200 into 10 raised to the Newton per mm square. That we are knowing. But when you are trying to manufacture a composite material, then the property would be different. Now metals are having isotropic property that we are considering. It means there is a homogeneous distribution of the material. But when you are talking about the composite, the distribution may not be homogeneous. Reason? Now there are certain reasons. The first reason you can say as the phases are different. So in a liquid phase of aluminum, it is not possible to put the silicon carbide on that particular manner. So that is why we are not getting the isotropic properties, and because of that these properties are going to get different. Okay, so that goes in the orthotropic material or anisotropic material. So that property gets changed accordingly. So you can say the density is definitely less for the composite if you see, and that is our interest. See, while maintaining the Young's modulus, you are getting the less density. It means your material weight is less. So that is our requirement, and that is the right now people are focusing upon. Okay. So, but if you talk about the other kinds of material, elastomer, if you go with in which our composite plastic composites are falling, so they are having very less density. While you can say the Young's modulus of those materials are also less, but that we are not focusing upon right now. Correct. So our focus is particularly with the particulate reinforced metal matrix composites. Now, there are a lot of applications of this material. There is a one important reason for this, that strength to weight ratio increases, as we have seen just previous, that modulus of elasticity is going to get increased. Correct. So, when you are having the requirement of higher strength, but as well as if we talk about the aeroplane, so aeroplane, while it is moving away from the center of gravity, then definitely the weight should be less. So whatever weighs less, it can fly easily, or the effort required is less, you can say. Correct. So people are trying to develop such a material so that they can reduce the overall weight of the aeroplane. So for that, if you heard about a number of satellites we have launched with the composite material, or we can say, which are weighing very, very less right now. So people are trying to develop those materials which are weighing very, very less. Now, if I simply tell you that the density of aluminum is, can anybody tell me what is the density of aluminum? Could anyone? Sir, are we able to take the responses?
Yes, sir, you can, but we are preferring that the questions will be
Okay.
taken after your presentations.
Okay, okay, fine. So the density of the aluminum is a 2.7 gram per centimeter cube, or 2700 kilogram per meter cube, you can say. But if you are adding some of the percentage of reinforced particle, that density gets reduced. Now that depends on the density of the particular reinforced material. Okay, so if you try those kind of material in this kind of application, definitely you would be able to reduce the weight of the component. And as and when you are reducing the weight of the component, the efficiency of any component could get improved. Okay, let's take the example of piston. So in generally piston, in previous times, let's say before 20 years back, we were using cast iron piston. So cast iron density is around 8,000 kg per meter cube. Correct. But if we use the aluminum alloy pistons, which is having density around 2,500 kilogram per meter cube, so definitely that improves the performance of an IC engine. Okay, and right now people are using the aluminum alloy, or the companies are also preferring the same material for the development of piston. Okay, so there is a lot of thing in the application point of view. If you talk about the structural, if you talk about any kind of machine beds, okay, so in that application we can utilize now preferably, see, aluminum alloy is preferable when you are having the less weight, when you want the less weight, or you can say the when you are having the requirement of thermal conductivity. So like in that thermal applications, you can even utilize the aluminum alloy. But when you talk about the titanium alloy, because titanium is somewhat costlier, so definitely you must have to see what is the application, and according to that you should use the titanium alloy. Okay. Now these are the basic classification of composite material. Now matrix base and reinforced base. Now we are not going to talk about the matrix base. Our focus right now is on reinforced base. So in reinforced base we're having fiber reinforces, which are fiber reinforced plastic, fiber reinforced composites. Okay, so carbon fiber based and a glass fiber based. Similarly, particle reinforced also, that is our interest right now, and structural also we're having in that sandwich or laminated. Okay, one by one layer if you put, you can able to produce the sandwich or laminated type reinforced based composite material. Okay, so we are particularly focusing upon the particle reinforced metal matrix composite. Okay, now the techniques of manufacturing, because the any material, conventional material, if you take, they are available as a ore type, and from ore we are doing the processing of it, and then we are getting the raw material, and then if you perform the casting, you are getting the solid material. You can say billets, generally we call it a raw material like a billets. But when we are talking about the composite material, it could not be manufactured by the conventional manners or conventional casting. Okay, because it the material what you are trying to add, the particular reinforced, that is not going to mix with each other. Simple अगर भाषा में बोले, अगर पानी के ऊपर मैं ऐश डालूंगा, फ्लाई ऐश, जला हुआ जैसे कागज जलाया आपने, if you try to mix it with it, it won't be possible. Okay, so whatever you can try, but वो easily mix नहीं होगा. Rather what you have to do, you can increase the density of the material, you have to increase the viscosity of the material, then you can mix it with it. And parallelly you need certain external force as well. And in a stir casting that we are going to talk about, the stir casting particularly is having a motor. Just see the attachment what we have provided, a simple furnace we're having, the normal pit furnace you can take, or any electrical furnace you can take. Okay, now a simple rod, you can say a shaft has been added, and at the end of the shaft we're having stirrer. ठीक है, दही बनाते हैं जैसे लस्सी बनाते हैं, वो सिंपल एक तरह का स्टरर है, बट डेफिनेटली इट इज ऑफ मटेरियल. Okay, now that impeller would be of, maybe you should keep the material which is having the temperature above the melting temperature of the casted material. मतलब जो मटेरियल हम कास्ट कर रहे हैं, डेफिनेटली यू शुड कीप द टेम्परेचर ऑफ द स्टरर, मटेरियल फॉर द स्टरर शुड बी, लेट्स से एल्यूमिनियम को कास्ट कर रहे हैं, then the material should be of SS or MS, which is having melting temperature of around 1190, around 1200 degree centigrade, correct? Now this is a crucible. Now in crucible we are putting our material which we are trying to mix. So initially we will put aluminium, correct? After that we will melt the aluminium, and we will add the silicon carbide at the top, and we will start the motor, and we will rotate the stirrer. Now what happens where you are having the stirrer, it rotates, and it the upper material will goes down, and bottom material which is at the bottom side, which tries to come up. Okay, so that is how we try to mix the silicon carbide with the aluminum, or the particular reinforced, maybe anything. It is not necessary you are using only silicon carbide. I'm just taking the example of silicon carbide. You can take anything. You can take magnesium oxide, you can take. Okay, aluminum oxide you can take. Certain other particle reinforced are available in market that you can take, but necessary that it should improve the performance of a material, or you can the strength of the material should be improved by using that. Okay, so when you try to mix it, and material will cool, correct? So when you are putting the material inside the mold, okay, it should have a proper directional solidification. Otherwise what will happen, a simple fundamental is there. When you try to rotate the material with the stirrer, it cools. Okay, because the stirrer provides the cooling effect is provided. So when you try to pour the material in the mold, it will solidify very quickly. So the directional solidification should be proper when you try to put in, correct? So that you have to make sure. So that is a part of a we can say experiment. Once you do it, you will come to know about this. So this is the simple setup of stir casting. Now there's another method of powder metallurgy, you can say. Now using powder metallurgy, in which material is fused, that is not melted, it is get fused with the parent material. So we're having powders we are mixing those powders with the parent metal. So these are the different particular reinforced powders, and we are mixing it with the parent powder. Again, please try to understand. In this case, we're having aluminum powder, not aluminum, let's say billet, we cannot use. It should be in a powder form. So once we mix it, then we try to compact it by applying a pressure, and then it goes to the furnace. Okay, so after that sintering, once you get the object is not in melting condition, it is of fused. So powder metallurgy is the best technique to manufacture metal matrix composites, but the reason people are not using it is the cost. So the people, like you can say, those who are doing the post graduation or PhD, they might not able to afford it, so that is why they are preferring the stir casting. But right now star casting is also giving the good results, if you talk about the distribution of the reinforced particle in the composite. Correct. Now the powder metallurgy technique, just what we discussed. Okay, so blending of the powders and then compaction, okay, and then hot pressing and then extrusion. So these are the processes we are following for powder metallurgy. Now this is the stir casting, as previously I showed. Okay, similarly over here we are doing. Now why we are doing this, why we are preparing such kind of material, there is always a reason that the property should improve. Now which property we are targeting particularly? So if we talk about that, we are targeting the hardness. Let's say aluminum, if you talk about, the hardness is around 50-55, you can say, that is in BHN. But if you improve, if you add some silicon carbide, that could get improved. Now you just see the micro hardness, it is in HV, weaker hardness. So 72 it is initially when the 0% of SiC is there, but as you add 3% of silicon carbide powder, the hardness could get improved. This is for the aluminum material. Now, if you add 5%, then it could go up to 98. And if you are adding 7%, it may go up to 112 weaker hardness. Now, uh, it is not like that if you add a 20% SiC and you are getting the same performance. No, that is not possible. Now, if you add more than 10%, this could get dropped and material completely become brittle. Okay, so that we cannot do. So this is again a trial and error that you should have, and you can have better performance. So 112, that is the weaker hardness we can receive at 7% of weight percentage of SiC. Now if we talk about the ultimate tensile strength, so look at here, at 0 we are getting 175 megapascal, but as we add 3%, we are getting 198. As we add 5%, we are getting 210. At 7%, we are getting 226. Now, this is again a question. When you go beyond 10%, what will happen? Definitely, the graph is going to get dropped. The reason being, finally, your material become hard and brittle, so the ultimate tensile strength would get reduced. You know about the stress strain curve for the brittle material and ductile material. So that is the difference, correct? So we cannot make the material brittle. Otherwise, the applicability of the material would get reduced. So वो भी हमें फोकस करना है, हमें वो भी सोचना है कि वो एप्लीकेशन में आना चाहिए, ठीक है, और हमें ये भी सोचना है उसकी प्रॉपर्टी भी इंप्रूव होनी चाहिए. सो दैट इज व्हाई वी शुड बी इन लिमिट. Okay, now this is the stress strain curve for the aluminum plus silicon carbide metal matrix composite. Just look at here at 0%, it means it's a pure aluminum. So the stress strain curve is like something like this. Okay, now once you add a 5%, 90% of aluminum and 5% of SiC, if you try to add, what will happen? You can see it is increasing, strain is increasing rather. It is going 3 up to 3 you are getting. Stress, it would be reducing, you can say. Further, if you try to increase, look at here. There is not a much change in that. And if further, if you try to increase up to 30% of SIC, if you go, then look at here, you may reach up to 3.5 megapascal, but there is no much change. Okay, so that much change we are not finding. But what is our focus? That material should be in the limit of ductility. Okay, you can say modulus of elasticity, or you can say the yield limit should be proper for the material. So you cannot go beyond that. Okay, so this kind of behavior we are not expecting. So that we should not perform. Let's say 30% SIC we should not go up to. Okay. So let us discuss some case studies I'm having, what we did till now. Now, this what we did in 2012, that we were evaluating the tool wear of ultrasonic machine for aluminum, silicon carbide, metal matrix composite. Now in that, the output variable what we were trying to measure was tool wear. Okay, and the input variable we have having composition of aluminum plus silicon carbide, different composition, let's say 5%, 10%, 15%. These were the variables. Thickness of the plates, amplitude of USM, and pressure. So these are the 4 variables we were having, and we will try to measure the tool wear. Now, once we manufacture the material, this is the EDS what we have received. EDS stands for electron dispersive spectroscopy. That particularly will give you the percentage results, whether the material, whatever you trying to put the particular reinforce in the parent material, whether you are getting it or not, or you can say the homogeneous distribution you are getting it or not. So this is for 10%. For 5% we were not able to achieve good result, but for 10% of silicon carbide and aluminum we have received 7.67 carbon percentage in that, and the aluminum would be of 85.24. Now this aluminum was 6061, and in 6061 you can say is the purest form of aluminum, you can say. So once we try to add silicon carbide in that, we have received even the 1.36% of silicon. तो अगर आप इसको ध्यान से देखेंगे तो 7.67 and 1.36 total, you can say around 9% is around something we have received. So 10% मटेरियल हमने डाला, उसमें से हमको 9% मटेरियल कंपोजिशन में मिला. So that is what you have to make sure when you are trying to put the material inside that. See, you are not sure whether material is distributed properly or not. So that we have to confirm by taking some tests. Okay, so this is the EDS test we have performed. We also performed the SEM and all that, and we have received good results. And that what we did in 2012. Now this was the result for that particular experiment, and the percentage SIC is more effective than the pressure for the tool wear. So it means this result says if you increase the brittleness of the material, that definitely it affects the tool wear. ओके, इसका मतलब ये है कंपोजिट मटेरियल को मशीनिंग करने जाएंगे तो टूल वेयर ज्यादा होगा डेफिनेटली. ओके, एंड as we are talking about the composite, where the material, you can say the reinforced particle are not distributed properly. Okay, that is not homogeneous, and that is why we are taking the you can say orthotropic or anisotropic property of that material. So this falls at the 3rd rank, the percentage of SIC, while amplitude was the highest you can say variable which is possible for the tool wear, and then the thickness, then silicon carbide percentage. So that falls in the at the 3rd rank. Let us move to the second case study. Now with 2 of our faculties, Chinmay Shah and Vijay Patel, we worked on the FSW, friction stir welding. So in that particular, what we were trying to do is optimization of FSW process parameter for aluminum silicon carbide particulate reinforced particle using ANOVA. So in that, we were trying to measure the ultimate tensile strength. That was our output variable or parameter, you can say. And input variables were having welding speed, composition of aluminum and silicon carbide, tool geometry, and tool rotation speed. So that what we tried to do. Now this is the setup which is available at PDPU Gandhinagar, and we performed our experiment over there. Now, uh, you can see the friction stir welding is a new kind of welding where having different tools are there. Uh, Whatever the plates you are trying to join, you are putting them in connection, and then you are putting the tool, and tool will move in a linear direction, and it is welding these two materials. Now, this two material is of aluminum silicon carbide composite, which we manufactured. Okay, so see, these are the variables, and C1, C2, C3, C. This is tool geometry for first one is that, second one is the taper tool when we used, third one is the threaded tool. So different tool we have used, and these are the four variables we were having, and we found the UTS, ultimate tensile strength, for 9 components. So we used the design of experiment for that, and the Taguchi technique we used to find out the ultimate tensile strength of it. Now, you can say, if you see it properly, UTS of friction stir weld is highly influenced by weight percentage of SIC. If you see this, okay, so weight percentage of SIC when it is 20%, then 93.3, that is the ultimate tensile strength we are receiving. While if you see at 10 percentage, it is 35.5. Okay, yes, there are also other parameter which are influencing it, but as the weight percentage increases of SIC, the UTS increases. That is a simple observation we were having. So this was the second case study. Now, the third one was with the aluminum oxide. The particle reinforced what we have used, what was aluminum oxide. Now that the work was optimization of process parameter of CNC milling for aluminum metal matrix composite. Again, my two colleagues were there, Vijay Patel and Nitin Mishra. Output parameter what we analyzed in that performance was surface roughness. And the input variable we were having the composition of aluminum and silicon carbide, and the speed, feed, and depth of cut. So as we were doing the work on CNC machining, definitely these were the you can say the standard variable that we have to take. Okay, now what conclusion we made from that particular experiment, that percentage weight of SiC and Al2O3. So this two reinforced particle has been utilized that influence the hardness of the metal matrix composite. Now, as the weight percentage increases, the hardness increases. But as I said in the graph as well, this is not true as you go beyond 15% or 10%. ठीक है, तो सब जगह ये सही नहीं है. This is, I cannot make the standard statement, but you can say up to 10% it will improve the hardness, but later on that will drop. So we conclude that with increase in percentage variation of SiC, particle surface roughness decrease. It means your material become rough. Definitely, because what happens certain times that your reinforced particle remain at the surface. देखो, मटेरियल को जब हम उसमें मोल्टन मेटल में पार्टिकल रेनफोर्स को डालते हैं, होता क्या है, मटेरियल सरफेस पे ही रह जाता है. And when you are having, I will show you that the improvement what we have received by changing the RPM as well. तो जब RPM आप चेंज करते हो, बढ़ाते हो मोटर के, स्टरर के, या फिर स्टरर का थोड़ा ज्योमेट्री चेंज करते हो, you might will receive a good result. Okay, so because of this reason, the particle remain on the surface, और वो surface पे आके चिपक जाते हैं, and that then they fuse with the material, and then they will give you the you can say rough surface they will provide you. Okay, so If you try to improve it, definitely certain parameters we have to change. Okay, now this is the setup still we are having, and we are still doing some performances on that. So this is the motor available, this is the pit furnace, and stirrer. You can see at the bottom side we were having bearing because it's a long shaft. So when we are having the long shaft, definitely you have to provide a bearing so that whatever the jerk or vibration you are getting, it can easily take in. Okay, लंबा shaft है तो vibration आएगा, so vibration absorb करना पड़ेगा, otherwise you can see the crucible is so small, and अगर vibration ज़्यादा आता है तो it might possible that the shaft will get stuck or strike with the crucible और वो उसको गिरा भी देगा. So one or two times that happened with us. Okay, so that's why we used to have that bearing at the bottom of this box. Okay, in box to hold the motor, some attachment or you can say clamp we have provided. ठीक है, एक क्लैंप को इधर से फिक्स कर दीजिए एंड यू कैन जस्ट पुट द मोटर इनसाइड, और देन यू कैन जस्ट स्टार्ट द बटन, या फिर आप स्टार्ट का बटन कहीं और रख दीजिए. यू कैन स्टार्ट इट बिकॉज द टेम्परेचर इज क्वाइट हाई व्हेन यू आर स्टैंडिंग अराउंड द फर्नेस. So uh, during casting, you just see this is the SS304 stirrer that initially we made in 2012. Okay, and that was used to manufacture the aluminum silicon carbide particular reinforced composite. So this was the setup we were having initially. Now, the very important thing that I have to discuss, that is the design of a stirrer. The number of different types of stirrer we made, but just look at here. This is the SS304 stirrer, which is having a 90 degree, you can say a simple is kind of a spur gear. ठीक है, simple अगर भाषा में बोले तो जैसे spur gear है. And this is the graphite stirrer, which is having 7 degree helix angle. Now, why to provide helix angle? Now you can understand, as this will try to rotate in clockwise or anti-clockwise direction, the material which is at the bottom side will try to go up, or it will push that material on upper side, and the upper side material will go on downside. Okay, so there is a complete flow of the material. So definitely we would get the best results, or you can say the homogeneous distribution we can receive easily. While in this case it is not possible. अगर आप इसको देखेंगे ध्यान से तो इस केस में ये पॉसिबल नहीं है. सेकंड थिंग, why to utilize graphite? The question may come that why to utilize graphite? Then see, sometimes what happen when you are trying to produce in a pit furnace, you cannot control the temperature sometimes. ठीक है, पिट में कभी कभी टेम्परेचर कंट्रोल नहीं होता है, और इट मे गो बियॉन्ड 1000 लेस से. अब अगर 1000 पे चला गया, सो SS304 रॉड जो है इट मे गेट मेल्ट. ओके, बिकॉज सी मार्केट जो अवेलेबल है SS304 के, दैट मे रेजिस्ट अप टू 1000. ठीक है, 1000 तक रेजिस्ट कर जाएगा, लेकिन अगर 1000 से ऊपर जाते हो आप, तो आपका स्टरर ही मेल्ट हो जा रहा है. तो हाउ कैन यू एक्सपेक्ट गुड रिजल्ट? नाउ SS स्टेनलेस स्टील इज हैविंग क्रोमियम एंड अदर कॉन्स्टिट्यूएंट्स, और इट इज ऑल्सो हैविंग, सो वो पूरा आपके मटेरियल में मिक्स हो गया. सो योर प्रॉपर्टीज आर गोइंग टू चेंज नाउ. ओके, so that is why the graphite stirrer we used, and graphite is having carbon, so it won't affect our results. Okay, हाँ, एक चीज है, ये ब्रिटल है, अगर ये थोड़ा सा भी इधर उधर टकरा है तो ये टूट जाएगा. that is the only thing we are having, or you can say the problem with the graphite stirrer. That problem we were not having with the SS rod. So two different stirrer we produced, and stirrer is the critical component when you are trying to prepare the material with the stir casting. So सबसे ज़्यादा critical यही है आपका चीज़. And I will show you now the third case study we were having. Now these are the copper silicon carbide metal matrix composite. Now copper is having melting temperature of 1084 degree centigrade. Now, in that particular, when we try to manufacture, we took 3 to 4 minutes for stirring. And the stirring speed we used to have variac, using that we can change our RPM. So we keep that RPM as at 450. Now blade angle is 90 degree, as I said, and total blades we were having 4. And the position of the stirrer we put up to 2/3 depth in the melt. हमने इसको 2/3 depth में डाला melt. Again, there might be a question if I show you the figure again. See, अगर आप ज्यादा ऊपर रखेंगे तो वो मेटल को बाहर फेंकेगा स्टरर, ठीक है, या फिर उसे अच्छे से मिक्स नहीं करेगा. सिंपली यू कैन सी, अगर इसे ज्यादा अंदर रखेंगे सो यू नीड मोर टॉर्क मोटर, फिर ज्यादा हैवी टॉर्क की मोटर चाहिए, बिकॉज इट्स अ डेंस मटेरियल, डेंसिटी ऑफ 3000 और 2700 किलोग्राम पर मीटर क्यूब. So for that kind of material, if you want to rotate, you should have a very high, or you can say heavy torque motor. So वो requirement बढ़ेगा. So the mechanism, or you can say the setup would become sturdy. तो वो थोड़ा rigid होता जाएगा. So that is why what we are trying to do, we are trying to have the better position for this stirrer as well. So उसको पूरा अंदर नहीं रखना है. Up to 2/3 depth you should move. And plate size we manufactured was 100 mm by 100 mm by 10 mm. Correct. Now this was the experiment we did, and you can see the results. Number of holes or cavities you can see. We produced a plate and we took a cross section of it, and then we received this plate. तो ये जो आया ये बीच में ऐसा है. You can see this. Number of cracks are there. Number of holes or pores are there. You can say. Okay. So that was the difficulty we received. We cannot test it, or we cannot utilize this kind of material. Now, whatever the defects we received, we analyzed them and we found that the distribution was heterogeneous. अब कॉपर के साथ एक और डिफिकल्टी है. कॉपर का डेंसिटी बहुत ज्यादा है, इट्स अराउंड 8900 kg पर मीटर क्यूब, और सिलिकॉन कार्बाइड का बहुत कम है. तो कोई तो ऐसी चीज अगर आप उसको मिक्स करना चाहो तो डेफिनेटली यू वुड बी फेसिंग द डिफिकल्टी व्हेन यू आर हैविंग अ लार्ज डेंसिटी डिफरेंस. ठीक है, जैसे मैंने पानी और फ्लाई एश का बात किया. तो दिस इज द फर्स्ट रीजन व्हाट वी हैव रिसीव्ड, द हेटेरोजेनियस डिस्ट्रीब्यूशन बिकॉज ऑफ द डेंसिटी डिफरेंस. सेकंड व्हाट वी फाउंड दैट द स्टरिंग स्पीड वाज लेस. ये थोड़ा हमें कम लगा कि ये नहीं हो रहा है अच्छे से मिक्स. इवन इफ यू सी दैट फिजिकली यू वुड फाउंड दैट ये सही नहीं हो रहा है. एंड थर्ड रीजन वाज अबाउट लेस स्टरिंग टाइम. एंड फाइनली द इम्प्रॉपर सॉलिडिफिकेशन. सो you can say we are not received a proper directional solidification. So that was the issue with this particular object. Now the improved results you can say. So this is the specimen of a copper silicon carbide particulate reinforced metal matrix composite, which we produced with the different parameters. Just give me a minute. Now the melting temperature of copper, that is not going to change. That is same while we change the stirring time. Now we stirred about 5 to 6 minutes. So initially it was 3 to 4 minutes. Now that we have changed to 5 to 6 minutes. We also changed the stirring speed. It was 450 rpm. Now we perform the experiment using 550 rpm. Now the important thing what we changed was helix angle. ये एक बहुत बड़ा चेंज था. The number of blades we kept it same, and the 2/3 depth, that is also we kept same. Okay, उसको हमने कुछ change नहीं किया, and the plate size we manufactured was same. Now you can see the result. Even if we took the cross section of the plate what we manufactured, and then we found this kind of plate we received. So you can see the change while we were having the difference, like this one, in which we were having the SS. Please look into this. This is of SS stirrer. Okay, and this is of graphite stirrer. So these are the two changes we made, particularly the stirring time, stirring speed, helix angle, and the graphite stirrer we used. So that gives us that homogeneous distribution we can receive if we utilize the graphite stirrer with helix angle. And now, uh, 5 to 6 minutes, this what we received for copper. अगर आप एल्यूमिनियम लेंगे so 3 to 4 minutes आर मोर देन इनफ. और आरपीएम भी जो हमने पिछली बार यूज किया था, that is enough. You cannot say like if you are whether you are performing with aluminum and the copper, and you are keeping the stirring time and stirring speed same. No, it is not like that. If you want this directional solidification and proper homogeneous casting, then uh, in aluminum you can reduce the stirring time. और एल्यूमिनियम का एडवांटेज क्या है? एल्यूमिनियम के साथ सिलिकॉन कार्बाइड अगर आप डालते हो तो सिलिकॉन कार्बाइड का डेंसिटी इज अराउंड 3000 केजी पर मीटर क्यूब, एल्यूमिनियम का है 2.7, यानी 2700 केजी पर मीटर क्यूब. सो डेंसिटी डिफरेंस बहुत कम है, एंड दैट इज द रीजन बिहाइंड द डेवलपमेंट ऑफ एल्यूमिनियम सिलिकॉन कार्बाइड मेटल मैट्रिक्स कंपोजिट. ये सबसे ज्यादा यूटिलाइज अभी यही हो रहा है. ये रीजन यही है कि डेंसिटी डिफरेंस दोनों में कम है. You can use MgO. Just yesterday we performed one experiment using MgO. लेकिन MgO का issue ये है that will melt at 600. अब वो तो मेल्ट हो जाता है, ठीक है, तो हम उसको ट्राई अभी नहीं कर सकते. ठीक है, मैग्नीशियम ऑक्साइड का मेल्टिंग टेम्परेचर इज टू लो, सो इफ यू पुट इन द एल्यूमिनियम मटेरियल तो वो तो मेल्ट हो गया, तो वो तो एलॉय बन गया. तो वी कैन नॉट हैव कंपोजिट मटेरियल ऑफ एल्यूमिनियम एंड MgO. Okay, so aluminum MgO you can produce using powder metallurgy. वो हमने ट्राई किया and we got succeeded. So using powder metallurgy you can try. Okay. So these are the large conclusion what we have received from our total whatever the case study we performed, that the effect of changing the constituents of particulate reinforce is affecting the strength of material. That already we have seen from the certain graphs. And silicon carbide is basically increases the strength of aluminum, but surface become poor. अभी surface अगर आपको सही करना है तो again you have to do machining and you have to perform the grinding, which is the costliest process you can say. And if you go with the high surface finish processes like honing, lapping, so it is again become costlier. So वो क्या होता है, जैसे ही आप सरफेस रफ बनाते हो, दो यू आर गेटिंग द बेटर स्ट्रेंथ, बट योर कॉस्ट ऑफ मशीनिंग वुड इंक्रीज इन, वो बहुत ज्यादा बढ़ जाता है फिर. ठीक है. नाउ द लास्ट वन इज द मैन्युफैक्चरिंग पैरामीटर्स आर आल्सो अफेक्टिंग द फाइनल प्रोडक्ट एज आई सेड. Okay, so certain what I have discussed, the manufacturing parameters like what kind of mold you have prepared, let's say whether you are prepared the metal casting you are doing, sand casting you are doing, shell molding, so that is also affecting it. ठीक है, तो वो सब प्रॉपर्टीज भी है. इफ यू टॉक अबाउट दी लेट्स से रिफ्रैक्टरीनेस इज नॉट प्रॉपर ऑफ दी सैंड व्हाट यू हैव यूज्ड, तो फिर वो आपको पोर्स देगा. अगर रिफ्रैक्टरीनेस सही नहीं है, अगर आपने मोल्ड नहीं बनाया है सही से, दैट इज आल्सो अफेक्टिंग इट. ओके, सो दोज पैरामीटर्स आर आल्सो इन पिक्चर once you try to manufacture it. Okay, so these are the some references what I've received. Those who are trying to work on this, I'm suggesting to use this particular paper. R Singh, he did a lot of work in the composite material. Okay, and lot of paper you'll find right now. Titanium alloys or titanium composites also people are trying to manufacture. ठीक है, Jatinder Kumar and Vinod Kumar, they also did a good work in this particular area. Now there's one video that I want to show. Please allow me. These are the few references what I've received, and later on we will take the questions. Just allow me to share the video first. I hope my video is visible.
Yes, sir.
Okay. See, that's how we started, and as you start the stirring, there's a fire, और वो कूल भी करता है, दोनों काम करता है. This is of aluminum and silicon carbide. Okay, so that is all from my end. If anyone is having any query, please you can ask.
If you have any question regarding this presentation about the metal matrix composite, you can unmute yourself and you can ask question if you have doubt or if you want to learn something. I think, sir, there is no question. So, thank you, Bhupesh, sir, for giving a good information about the metal matrix composite and the some scope that that can be contributed for the research work actually. So,
Thank you so much.
once again,
Thank you so much, DC Banswara, for inviting me for this, for giving me the opportunity to deliver a lecture on star casting. Even now, अगर नहीं अभी query, later on if you want to ask anything, I can give my email ID to you, to Jignesh sir, so that any query further or students wants to work on the composite material, they can directly drop a message to me. Okay, so कभी भी आपको help चाहिए इस चीज के लिए, so I'm always there.
okay, sure. And thanks to each and every participant, those are connected with us. And now our next session will be at the 3 p.m. So I request all the participants, please be connect at the 3 p.m. with the same Google Meet ID. Okay. Thank you, each and everyone. Thank you, Bhupesh sir.